So, we will continue with the shading devices that we did other day, right. Now, we talked about efficiencies. Remember that shading efficiency, HO, SP and then HE, etc., etc. So, we defined certain shading performance efficiencies. Now, supposing you want to calculate out for the whole year how much is the heat is being blocked, then one can do through this external shading multipliers, right. So, what we have seen is that we have already seen that shading is very important. This we have already seen as it is stated here. So, using horizontal shading or overhangs or the side fins, vertical fins or combination we can use, and then we can cut down the solar heat gain in summer, and also the dimensions can be optimized in order to minimize the summer gain and maximize the winter gain, right. The difference between the two with a weightage factor of half for the winter gain. So, that is what we have seen earlier, right. So, this can be like for the year, if we want to calculate out this, you can use this external shading multipliers, which are nothing but a factor. Now, some of the regulatory yardsticks, for example, many international codes, right, or many codes, in fact, many countries' code might restrict, look, the amount of energy you can, by design, envelope should be designed or the building should be designed in such a manner that maximum cooling load per unit area should not be more than something. This is one of the straightforward yardstick, that maximum energy consumption per unit floor area should not be more than something, but this is relatively difficult, people have not done that way, but there are certain other yardsticks. For example, our code ECBC, Energy Conservation Building Code of India, what it does is it says it gives you certain prescriptive guidelines, says U value of wall should be this much, etc., etc., right. Also it gives you kind of some trade off between different, there are some philosophies are there, and performance based design also. But there is one used in Hong Kong, Singapore, etc., they call it OTTV, overall thermal transfer value, and again they restrict this. I am not going to discuss about OTTV in this class, but there this shading multipliers are used, external shading multipliers are used, right. So, external shading multiplier is defined as a ratio of total solar gain received through a window shaded by an external shading device to that received from the same window if it was completely unshaded. Now, remember HO, you must be remembering sometime I talked about HO, right. HO was the, that is right, we defined, we used something like HO, then we used HE, etc. What was HO? What was HO? During the overheated period, right, divided by, then we use the total incident upon it. So, if I want to calculate that sort of a thing, then this philosophy that, or rather the algebra we are talking about, this becomes important. So, you can see the similarity. It is the solar gain received through the window shaded by an external shading device to that received from the same window if it was completely unshaded, right. So, it is a ratio actually. So, total solar gain through a window shaded by an external shading device is obtained as the sum of the total solar radiation on an exposed surface and diffused radiation received on shaded surface multiplied by their respective areas. So, it is basically intensity of radiation, both diffused and direct, multiplied by the area. So, solar gain through the window shaded by an external shading device is obtained as the sum of total radiation. So, let us see how it is. The algebra is not very complex. So, you can think in terms of a wall, and this is the altitude angle, this is the normal to the wall, right. This is normal north, due north and due south, this is normal to the wall. This is the sun ray, its projection onto the ground is this is normal to the wall. This is normal to wall, normal to the wall, and this is basically south direction and north direction. So, what is this angle? This is phi, solar azimuth. This is solar azimuth, going clockwise from this direction, solar azimuth. And normal to this surface is this. So, this is nothing but this complete thing is wall azimuth. So, difference between these two, this gamma is nothing but wall solar azimuth, right? Wall solar azimuth. So, gamma is wall solar azimuth. This is projection of the sun ray onto the ground. So, therefore, this is altitude angle, this is altitude angle, right. So, altitude angle, wall solar azimuth, and phi of course is a solar azimuth as we have seen, right. So, solar altitude angle, wall solar azimuth, and just is this the azimuth angle. Since we have used earlier notation beta, gamma and phi, I would like to concentrate on the same notation even now, and that is why I have changed this, although my slide said something different. Now, then vertical shadow angle, actually we have used epsilon earlier as an angle between two planes, the horizontal plane and an inclined plane projected through the sun. So, what is vertical shadow angle? Vertical shadow angle is, vertical shadow angle is that angle when sun ray is just blocked. Remember that is what we talked about. This is the this is the vertical shadow angle. Vertical shadow angle is this. This is let us say end of the wall, but the sun ray might fall, just gaze through it and fall somewhere there, right. And our relationships were also there. So, tan of, we call that epsilon, here it is written as theta 1, tan of theta 1 is equals to sec of, remember we had the relationship tan beta sec gamma, I think that is what it was, sec gamma and tan of altitude angle. Remember that we derived this earlier, tan epsilon is equals to, right. So, I am just using different notation. So, same concepts we can use here, same concepts we can use here, actually same concepts we can use here. So, this like let me use a different color, this is for the sun ray is falling like this. So, projection of the sun ray is somewhere there, right. This is normal to the surface, this is gamma, this is beta, right, and this is my epsilon. So, we obtained a relationship in the last class, I think something like this, and we will make use of this here itself. So, tan theta 1, so that is what it is, tan vertical shadow angle is given by expression tan theta 1, we used epsilon, actually here we are using theta 1 is equals to epsilon, that is what I am saying. So, tan beta multiplied by sec of gamma, that is what it is. To calculate the shading coefficient of vertical fins and projection, horizontal shadow angle was, we are calling it theta 2, right, here is equals to simply gamma. Is a horizontal shadow angle, you remember we talked about that, because this was the case of a vertical fin, something like this is the window, there is a vertical fin of this kind. So, this is the normal to the wall, this is normal to the wall, and this is the sun's just at the point when sun just touches. Beyond that, on this side it will block the sun completely. On this side, when the sun is in this side, it will block the sun completely. Here it will not block. So, it is exactly at that time, particular time. So, that is what we are calling as horizontal, horizontal shadow angle, and this is nothing but this is the sun rays here on plan, this is normal to the wall. So, from north if you come here, this will be your phi and this will be your wall solar azimuth, difference between them. So, this is simply wall solar azimuth, wall azimuth, difference between wall azimuth and solar azimuth. So, this theta 2 is equals to gamma, that is horizontal shadow angle is simply is equals to gamma. Remember that we discussed that in the last class earlier. So, this we understand, you make use of them again, alright, we make use of them. So, the next is the determination of fraction of window area exposed to the sun given by a factor g. Vertical shadow angle is always positive, because it is like that, right. So, it will be always positive, vertical shadow angle will always be positive, it cannot be negative, because it is from the horizontal ground to vertically upward, touching the tip of the shading device, right. So, this is always positive, and vertical this vertical shadow angle is always positive, and horizontal shadow angle, which is for the vertical fins or shading devices, it is positive if it is to the right of the wall, and it is negative if it is to the right of wall orientation, negative if the left of wall orientation. What I mean to say is, supposing this is my window, right, this is south direction, this is my window. Now, I have a fin here, I have a fin here. So, morning sun will be blocked, morning sun starts from here, the moment it comes here, it will be, it will not block any further, right. So, this is on the right hand, what we are saying is positive if it to the right of the wall orientation. So, if it is on the right of the wall orientation, so this is positive, and in the afternoon, the moment sun passes this area, because this is west, this is east, right. So, again it will be blocking the sun's ray, right. So, this will be another horizontal shadow angle, this will be another, generally they are same because it is symmetrical. If it is facing south, they will be same. If it is not facing south inclined, then of course it may be different, right. If it is facing due south, normal to the south, normal to the wall is towards the south, then it will be actually equal, but it can be. So, this is negative, this portion is, this we are calling as negative, this zone is positive, this is negative, this is positive, all right. So, this is by definition. So, that is what it is, positive and negative as shown here. So, this is positive and negative, that is how we are defining it. If it is right of the wall, then it is positive, left of the wall, then it is negative. Now, let us make it a little bit general. Supposing sun is here, P is the, see all the time it will not be blocking the sun. You design for the extreme condition, that is what we said in the last class. We said that we find out the overheated period and underheated period, and then try to find out corresponding to that what would be for a given length, how much it would block during the overheated period, and how much it will actually block during underheated period. Half of that we can take and divided by the total received, that is the efficiency, and we can maximize that. So, we will have some length, right. So, it will not block all the time, either it is horizontal shading device, horizontal shading device or vertical shading device, whichever it is, it will not block the sun all the time, it will block only sometime it will block. So, how much it blocks, that is what we are trying to find out. Now, supposing it is a little bit generalized, supposing this is inclined, shading device is inclined, I said that shading device can also be inclined, its effective length becomes actually more. Then this portion sun is here, then this will block, AS will be the one which will be blocked, AS is blocked, AS is blocked, AS is the area of the window which is blocked. I mean, we are assuming vertical windows, so width will be, width multiplied by this length will be what is blocked, right, or it is the length ratio I can find out, and this is the portion where solar radiation is received, and this is the total, right. So, this is the portion where solar radiation is received, this is what is blocked, and this angle, this angle is theta, this angle is theta 1, this I am calling as phi 1, this angle is theta 1, this angle is phi 1. Theta 1, why theta 1? It corresponds to epsilon at that time. I mean, epsilon is for design purposes we are using epsilon. So, theta 1 is same as epsilon at any time I am calling it theta 1. So, at this particular time, what was the angle? Angle of from the tip to the normal, this angle is same as this angle theta 1, right. So, this is the corresponding vertical shadow angle, because that by definition, if I draw a line to the tip of the shading device and the angle it makes it the horizontal, because this is the portion up to which it shades, rest all it does not shade. So, corresponding to this is the angle which is equals to theta 1, which would have been epsilon at some period of time, for design purposes we are using epsilon. So, this will be same as, because this line and this line is parallel, this is same as theta 1. This is phi 1, I am calling it phi 1. So, phi 1 is the angle of the shading device with the, it makes it the horizontal plane. So, this is the horizontal plane, this is how it So, phi 1 is the angle, this angle and theta 1 is same as theta, this angle. I want to find out this ratio of this AS by AT at any time. At any time I'll like to find out. Now altitude angle of the sun will be known at any time, azimuth angle of the sun will be known at any time. So I should be able to find out, right? Is the conceptually is it clear what I am talking about? So AS then is equals to, from geometry simply, AS is equals to P, P sin theta, right? P is this length of the inclined shading device is P. So how much is this one? AS is equals to this plus this plus this, right? So this is, how much is this one? This is P sin theta, P sin, phi sin phi, phi 1, sin phi 1, because this angle I am calling as sin phi 1. And how much is this? How much is this? This is known to us, or P is known to us. So if P is known, this is P cos phi, and this angle is theta. So this by this is equals to tan theta 1. So P cos phi 1 tan theta 1, right? So AS is equals to P cos phi 1 into tan theta 1 and psi phi 1, right? Now theta 1 I can find out. Phi 1 is a permanent thing. It's a permanent feature because inclination is fixed. It's a passive feature. It is fixed. Theta 1 will be a function of altitude angle and azimuth angle of the sun. Wall solar azimuth and altitude angle. It will depend upon that, because we have already found out that was equals to tan theta 1 is equals to tan beta, right? Right. So if that is the case, secant gamma, this is wall solar azimuth, which depends upon altitude angle and azimuth angle, right, and wall azimuth. So basically we can find out from the it depends upon azimuth angle and wall azimuth, sun solar azimuth and wall at that particular time. It will be a function, this AS will change with time, because some other time the sun will go there, so sun goes there, it blocks this much. Some other time sun goes there, so it blocks somewhat less, so and so on and so forth. So portion of the, you can find out the area of the, and this is function of time, hour angle, declination and latitude angle and wall orientation. This is again hour angle, latitude and declination. So therefore function of the time of the day in a year, on a given day, etc., at a given location. So this we can find out, and therefore AS you can find out as a function of the time. AS you can find out as a function of the time. AS you can find out as a function of the time, right? So that's what you can do. Now you can sum it up for the whole year, every hour. Obviously you'll have to use a repetitive calculation, so you have to write a small program or Excel sheet or whatever you like it, so that's right. So this you can sum up. So G factor is continuous horizontal, for a continuous horizontal shading device fixed at window head level, projected an angle is given by this. AE is equals to, total is AF, total fenestration height, or area is AF, minus AS is AE, is what is receiving the radiation, that multiplied by intensity of radiation at that particular time. Both are function of time. You can sum it up for the whole year. So P is the length of the shading device, E is exposed area, shaded window, total is this. Now we can find out actually. So G is the ratio of AE by AF, and which is 1 minus this, we have found out, 1 minus this, because AS was this and AE is AE by AF. So AE is AF, if I am dividing by this, I will get 1 minus AS by AF. So fenestration area is known to me, this ratio I can find out, right? This G multiplied by I is the radiation received, G multiplied by I at given time. So G is a function of time, I is a function of time, and we know how to calculate out for any surface. So I into G, sum it up for all, you can find out. I will come back to this again for the horizontal one. So you see this sum up. So external shading multiplier is G and I direct, and if you have diffused, which will come from half of the hemisphere, diffused will come from half of the hemisphere, because vertical one it doesn't see the full hemisphere, only one side. Supposing it is facing south, so it will see two quadrants, southeast and southwest. So total diffuse sky radiation is known, half of it can be taken. So that will be I diffuse, this is I direct, right. Beam radiation, which is global, minus diffuse, we talked about that sometime earlier. So this we can do, and we can do it from hour 1 to all the hours and sum it up, and the total received onto the surface, if there was no shading, that I can find out. So this is called external shading multipliers, and the HO etc. other day we looked into, you can calculate out using same procedure. So this was for horizontal shading device. Now if it is a vertical shading device, we go here for vertical shading device, right. This is what we looked into. So for vertical shading device, now again I take an inclined case, which is more general, and what is this? This is theta 2, and this I am calling as phi 2, which is a permanent feature. Phi 2 is a permanent feature, this angle is a permanent feature, because inclination is constant, it is a passive feature. So this is phi 2, this is what we are calling is theta 2, which will be equals to gamma at particular time. This is exposed area, this is the shaded area, and total is of course this area, total is this area, total is this area. P is the length, exactly in the same manner that we have done earlier, exactly in the same manner that we have done earlier. Notations are same. G factor we can find out, same as we have defined. Now, okay, I'll first come to this. So this is my P length. I want to find out this. So how much is this actually? This first I should be able to find out A total. A total. This is P. This is P. I want to find out, this angle is known to me. So this is theta 2 plus theta 1, theta 2 plus theta 1 actually. This is 90 degrees. So if I want to find out, I am interested in finding out this to sum. This I can find out very easily. This is P, this is basically theta 2. So this is P sin theta 2, right. P sin theta 2 is this one, sin theta 2 is this portion, and I want to find out this portion. Then what I got to do is, this is theta 1, theta 2, or first is this one, this is my phi 2, right, because it is a permanent feature, this inclination is constant. So P phi 2, P sin phi 2 is this much, P cos phi 2 is this, P cos phi 2 10 theta 1 theta 2 plus phi 2 will be this length. So let us see what we have done. Theta 2 should be this whole angle, theta 2 should be this whole angle. So this one, if I want to find out, tan of theta 2 will give me that, tan of theta 2 will give me that. And how much is this? This is cos of phi 2. So P cos phi 2 tan theta 2 would be this full length, and this will be simply P, this will be sin phi 2, yeah, P sin phi 2, P sin phi 2. So P cos phi 2, yes, this is to be subtracted, this is to be subtracted, this has to be subtracted, but this will get subtracted depending upon the direction of, because we said it is positive and negative. So it will automatically get subtracted accordingly, right. So this is fine, this is all right, this is all right. So general form of this equation will still stand as the same one, cos phi, this is 1 minus exposed area, and this has to be subtracted, right, depending upon whether the shading is on the left of the, left, like we defined this earlier, so it will automatically get actually subtracted depending upon left or right. Supposing it is on the right, my shading is something like this, right, shading is something like this. It will depend upon that, and depending upon that actually sin phi and theta as taken according to the sign convention, if you take it, either it will be plus or it will be minus, depending upon where the shading is actually corresponding to the window, where is shading corresponding to the window. That is how we defined actually. If you recollect, this is how we define, the angles were defined. This is defined positive or negative. If you feel you are confused, then you take the absolute value, but you have to do the addition or subtraction. You have to do it accordingly, yourself you have to do. Otherwise, this sign is positive or negative depending upon angle theta 2 being positive or negative. It will depend upon sign, this being positive or negative. All right. So that's how we can calculate out. And if we find out G, if we find out G, then if we find out G, the same thing. So for whole of the year you can repeat this process. For whole of the year you can repeat this process, and you can find out what is called external shading multiplier, which is a ratio, right, which is a ratio. Or else you can also use them for designing the shading device, because this will correspond to, you are taking the total radiation that is being blocked. So yearly heat efficiency, remember we talked of yearly heat efficiency, that was the ratio of the energy block divided by the total falling onto it. Actually this is something similar to yearly heat efficiency. But supposing you only want to find out for summer months, you can do that as well. You want to find out for winter months, you can do. So this is a generalized formula that gives you how to calculate out.